Dear students, hope you all are well at home and enjoying the e-learning. Today, I welcome you all in lecture 18. Before starting the today's lecture, let's have a quick recap of the previous lecture. Yesterday, we have discussed in the addition reaction the nucleophilic addition reaction, in which we have discussed about its definition, the detailed mechanism of the nucleophilic addition reactions, in which we have learned about the effect of nature of nucleophile on the mechanism of the nucleophilic addition reaction, in which we have learned the effect of strong nucleophile and the weak nucleophile. Then after, we have learned about the comparison of the reactivity of aldehyde and ketones towards the nucleophilic addition reaction, in which we have learned that aldehyde are more reactive than the ketones towards the nucleophilic addition reaction. Then we have discussed some examples of the nucleophilic addition reactions in the carbonyl compound. Now let us start the today's lecture. Today we are going to learn about the free radical addition reactions, and also we will going to start the new topic substitution reaction, in which we will be learning about the nucleophilic substitution reaction SN1 reaction in the detail. So let us start with the free radical addition reactions. Students, we have earlier learned that the addition reactions in organic compounds are of three types: electrophilic addition, nucleophilic addition, and the free radical addition reactions. Electrophilic and nucleophilic addition reactions we have learned earlier. Now today we are starting with the free radical addition reactions. It was observed that in presence of peroxide, the addition of hydrogen bromide to unsymmetrical alkene takes place in an anti-Markovnikov manner. That means, as we have earlier learned in lecture 16, that when addition of the HBr takes place on unsymmetrical alkene, the hydrogen goes on the carbon atom which already having the maximum amount of hydrogen. So as per the Markovnikov rule or Markovnikov addition, the product should be the 2-bromopropane. But it was observed that if this reaction taking place in presence of peroxide, instead of forming the 2-bromopropane, the product is formed is 1-bromopropane. This was discovered by the famous chemist Kharash, and therefore this effect is named as the Kharash effect or the peroxide effect. Now the question comes, why it's so? Why this 1-bromopropane is obtained? That means, why the addition of HBr in presence of peroxide taking place via anti-Markovnikov addition? The reason behind this is that in presence of peroxide, the addition of HBr to unsymmetrical alkene taking place with the free radical mechanisms, while this attack in absence of peroxide taking place with the electrophilic addition mechanism. That means the ionic mechanisms, while in presence of peroxide the mechanism followed is the free radical addition mechanisms. So let us discuss the mechanism of the free radical addition reaction. The free radical addition reaction follows the chain mechanisms, and we know the chain reaction involves three steps, that is chain initiation step, chain propagation step, and the chain termination step. In the first step, that is the chain initiation step, the peroxide, this is the peroxide, since the peroxide contains weak oxygen-oxygen bond, so by application of heat or the light, it undergoes in the homolytic fission. This We have learned earlier about the homolytic fission. So due to the homolytic fission of the peroxide, there is the formation of the hydroxyl radical in the chain initiation step. This hydroxyl radical now attacks on the attacking species. In this addition reaction, the attacking species is the HBr. So this peroxide attacks on the attacking species and bromine radical is formed in the chain initiation step. So what is the chain initiation step? In the chain initiation step, the peroxide breaks with the homolytic fission and formation of the hydroxyl radical or the alkoxy radicals, and due to the attack of this radical on the attacking species HBr, formation of the bromine radical takes place in the chain initiation step. Next step is the chain propagation step. In the chain propagation step, the bromide radical formed in the first step attacks on the unsymmetrical alkene. So if it attacks on unsymmetrical alkene, look at this reaction here. This bromine radical may attack on the carbon atom number 1 and on the carbon atom number 2. So if it attacks at the carbon atom number 1, that means attack like this here, then the free radical comes to the carbon atom number 2. So formation of the secondary radical takes place. While consider that when this bromine radical attacks on second carbon atom, so this bromine forms the bond with the second carbon atom and radical is present here. So formation of the primary radical takes place. That is the reason why bromine attack on the carbon atom number 1, that is the least substituted carbon atom, because the attack on this least substituted carbon atom give results in the formation of the more stable free radical. That's why bromine adds up on the least substituted carbon of the alkene. Hence the addition of the HBr in peroxide taking place via anti-Markovnikov manner. I hope it is now clear to you all. Third step is the termination step. In termination step, combination of the different radical may takes place. For example, two bromine radical combined to give the bromine, or bromine combined with the alkyl free radical, or two alkyl free radical may combine. But this radical addition of bromine to alkene by radical addition reaction will go on until all the alkene turns into the bromoalkane, and this process will take some time to finish. So chain termination step, we do not concern about this step because our concern is mainly to this step. One more thing to be remembered while discussing the free radical addition reaction, that HBr in presence of peroxide gives the anti-Markovnikov addition, while HF, HI and HCl do not give this type of reaction, because HF, hydrogen fluoride, and HCl having the greater bond energy. That's so these cannot splits into the radical, chlorine radical or the fluorine radical, while HI has the lower bond energy than HBr, but the alkyl radical that forms due to the addition of the iodine radical is unstable and quickly loses the iodine radical to regenerate the alkene. That's why only HBr gives the anti-Markovnikov addition, or HBr shows the peroxide effect or the Kharash effect. HF, HI and HCl do not show this type of addition reaction. Some other examples of this addition, free radical addition reaction, are addition of polyhalomethanes to alkene, addition involving acyl halides to alkene, and addition of thiols and thiocarboxylic acid to the alkene in presence of peroxide. So let us summarize the free radical addition reactions. Free radical addition reactions takes place with the chain mechanisms which involves initiation step, propagation step and the termination step. And since in the propagation step formation of the more stable free radical takes place, that's why addition occur anti-Markovnikov addition. Second important point is that HBr in presence of peroxide reacts with the free radical mechanisms to give the anti-Markovnikov orientation of the product. This is due to the attack of bromine radical to the least substituted carbon and formation of the more stable alkyl radical. That's all for the free radical addition reaction. Now it's time to check your learning. Look at this question here. In which of the following will Kharash effect operate? First option, second, third and fourth. Please pause the video for a minute and think about this question. Yes, first is the correct option. Why? Look here, in option second and option 4, Hi and HCl is the attacking species, and we have learned that both of these do not give the peroxide effect of the Kharash effect. So option 2 and option 4 are ruled out. Now remaining options are option 1 and option 3. In option 3, the alkene is the symmetrical alkene. So when HBr adds on in this alkene, either in presence of peroxide or in absence of peroxide, the same product is formed because it is the symmetrical alkene. Hence it also ruled out. So the correct answer is the option A. Now let us start with the substitution reactions. As we have earlier discussed in lecture 16, the substitution reaction involves the direct replacement of an atom or a group of atoms in an organic molecule by another atom or group of atoms without any change in the remaining part of the molecule. So here it is the replacement of hydrogen by the chlorine, and remaining part CH3 is the same. This is the example of the substitution reaction. Remember, the substitution reaction in organic compounds takes place at the sp3 hybridized carbon atom, that is alkene, haloalkanes and the alcohols, and at the sp2 hybridized carbon atom of the benzene. So these are the compounds which shows the substitution reactions in organic chemistry. Next is the types of substitution reactions. On the basis of the attacking reagent, the substitution reactions are of 3 types: electrophilic substitution reactions, nucleophilic substitution reactions and the free radical substitution reactions. But obvious, when the attacking species is the electrophile, then it is called the electrophilic substitution reaction. While when attacking species is the nucleophile, then it is called as the nucleophilic substitution reaction. And when the substitution takes place with the free radical attacking species, then it is called the free radical substitution reaction. So let us first start with the nucleophilic substitution reactions. The nucleophilic substitution reactions are those in which the attack of nucleophile on the saturated carbon atom having the substituent group results in the displacement of this substituent group from the parent molecule. So look at this reaction here. This nucleophile attacks on the carbon atom here, and this X, that is the substituent group, leaves the carbon atom or the parent compound, and nucleophile forms the bond with the carbon atom, and substituent group X leaves the parent compound as the leaving group. So the compound on which substitution takes place is called the substrate molecule. So this is the substrate here, This is attacking species, and the substituent group which is displaced from the parent compound or the substrate is called here the leaving group. So in this reaction, this is the substrate molecule, this is the attacking species, and X is here the leaving group. These nucleophilic substitution reactions may proceed with the different type of mechanisms. So depending upon the mechanism, the nucleophilic substitution reactions are of 4 types, that is substitution nucleophilic unimolecular SN1 reaction, substitution nucleophilic bimolecular at SN2 reaction, substitution nucleophilic intramolecular, that is SNI reaction, and aromatic nucleophilic substitution, that is SNAR reaction. We will be discussing all types of mechanisms in detail. So let us start with the substitution nucleophilic unimolecular reaction. Substitution nucleophilic unimolecular reaction, that is SN1 reactions. The SN1 reactions proceed with the formation of the carbocation intermediate, and the product is obtained as the racemic mixture. Both of these points are the very important points with respect to the SN1 reaction. So let's look the mechanism first. The first step of the SN1 reaction is the ionization of the substrate molecule. Let us take the example of the bromobutane here. In the first step, the bromobutane ionizes and formation of the carbocation takes place. This is the slow step, hence it is also called the rate determining step. Remember, it is the rate determining step of the SN1 reaction. In this step, formation of the carbocation takes place due to the ionization of the substrate molecule. In the second step, the carbocation is attacked by the nucleophile. What is nucleophile here? Here nucleophile is the H2O molecule. It is the solvent molecule. Hence, the carbocation formed in the first step, the carbon atom which having the positive charge act as the nucleophile, and the solvent molecule H2O, due to the presence of the lone pair of electron, act as the nucleophile. So in the next step, this nucleophile attacks on the electrophilic carbon of the carbocation formed in the first step, and formation of the oxonium ion takes place. This is the oxonium ion. In the third step, the positive charge on the carbocation was shifted to the oxygen here, and the oxonium ion is formed in the second step. So in the last and the third step, the water solvent is now act as a base and deprotonates the oxonium ion. That means it removes the proton from the oxonium ion, this, and formation of the hydronium ion takes place, and final product alcohol is formed. So let us look again. In the SN1 reaction, first step is the formation of the carbocation by the ionization of the substrate molecule. In the second step, attack of the nucleophile takes place on the carbocation formed in the first step, and formation of the oxonium ion takes place. And in the last step, this base, that means the solvent molecule H2O, deprotonates the oxonium ion, and formation of the final product, that is the alcohol, takes place. Now, question arises that why SN1 reaction results in the formation of the racemic mixture? Why it is so? We can obtain the answer of this question by studying the stereochemistry of the SN1 reaction. we just now discussed that in the first step of the SN1 reaction, there is the formation of the carbocation takes place. This carbocation is having the carbon atom which is in the sp2 hybridized state. Hence, due to this sp2 hybridization, the geometry of the carbocation formed is the trigonal planar. Therefore, the probability, due to its trigonal planar geometry, probability of the nucleophile attack is equal from the left hand side as well as from the right hand side. So nucleophile can now attack from both sides equally. So it is the probability that it may be formed the dextrorotatory product or the levorotatory product in the equal amount. That's why racemic mixture is formed in the SN1 reaction. Remember one thing, due to the formation of the carbocation in the first step, and hence the geometry of the carbocation is the trigonal planar. That's why this causes the probability of the attack of the nucleophile from both sides is equal. Left hand side it may attack or right hand side it may attack. Therefore, dextrorotatory and levorotatory products are formed in the equal amount. Hence, in the SN1 reaction, racemic mixture is formed. Now, second important point about the SN1 reaction is the effect of solvent on the SN1 reaction. A solvent that can facilitate the formation of the carbocation intermediate will increase the rate of SN1 reaction. That means all the solvent which favors or which promote the formation of the carbocation intermediate will increase the rate of SN1 reaction. The preferred solvent for this type of reaction are both polar and the protic solvent. Why? Because the polar nature of the solvent helps to stabilize ionic intermediates. That means polarity of the solvent increases the stability of the carbocation formed, while the protic nature of the solvent helps solvate the leaving group. That means reaction can be possible through SN1 mechanisms. Example of solvent used in SN1 reaction are alcohol and the water, because these solvents also act as the nucleophile. Now it's time to check your learning. Which step in SN1 reaction is a slow rate determining step? Attack of nucleophile, formation of a racemic mixture, formation of carbocation, or all are the rate determining step. Pause the video for a minute and think about this question. Yes, the correct answer is the formation of the carbocation. As we have earlier discussed that in SN1 reaction, first step is the formation of the carbocation, which is the slow step, and due to this slow step it is also called as the rate determining step. So third option is the correct option. So let us summarize what we have learned in today's lecture. Today we have learned about the free radical reaction mechanism, in which we have learned that due to the peroxide effect, addition of HBr on the unsymmetrical alkenes in presence of peroxide takes place in anti-Markovnikov manner. Next we have discussed today the substitution reactions, in which the definition and the various types of substitution reactions we have discussed. We have learned about the nucleophilic substitution reaction, electrophilic substitution reaction, and the free radical substitution reaction, in which we have started today with the nucleophilic substitution reaction in the detail, and learned that depending upon the mechanism, the nucleophilic substitution reactions are of four types: SN1 reaction, SN2 reaction, SNI reaction and SNAR reaction. And we have started the detailed mechanism of the SN1 reaction today, in which we have studied in detail the mechanism of the SN1 reaction, in which we have learned that in the first step of the SN1 reaction, the carbocation formation takes place. It is the rate determining step. In the second step, there is the formation of the oxonium ion, and in the third and the last step, deprotonation of the oxonium ion results the formation of the desired product. Then we have learned about the stereochemistry of the SN1 reaction, in which we have learned that since the formation of the carbocation takes place in the SN1 reaction and the molecular geometry of the carbocation is the trigonal planar, which allows the nucleophile to attack from the both sides to the carbon atom, hence racemic mixture is formed in the SN1 reaction. And then we have learned the effect of solvent on the SN1 reaction. We have learned that the polar and the protic solvent favors the SN1 mechanism. I hope this lecture find helpful you all in understanding the basic concepts of the free radical addition reaction and the SN1 reaction. Thank you. Take good care of yourself and stay safe and healthy at home. Thank you.